A diver's incident log from a tropical reef begins with a detail that would seem minor on land. A brief step in shallow water, a sudden surge of pain, and a rapid loss of control in the leg. Within minutes, the injury escalates, not because the wound is massive, but because venom, water pressure, and delayed extraction work together. In forests or savannas, danger often announces itself with sound or movement. In the ocean, some of the most dangerous animals never need to chase you at all. On land, the threats humans fear most are familiar and visible. Lions, wolves, bears, and venomous snakes rely on teeth, strength, or a bite that usually requires direct provocation or proximity. Even then, gravity, footing, and air give the human body options to fight, flee, or stabilize. In the ocean, a box jellyfish can deliver cardiac-threatening venom through near-invisible contact, and a reef stonefish can inject toxins simply by being stepped on. Lethality shifts from pursuit to chemistry, and from confrontation to accident. Marine predators and defenses are shaped by an environment where escape is slower and mistakes linger longer. A great white shark may rarely attack humans, but when it does, blood loss in water becomes harder to control than on land. A stingray's barb can cause intense pain and tissue damage without any predatory intent, while a needlefish can impale at speed because water allows momentum without friction. Even animals that seem passive, like pufferfish, become lethal through toxins that act hours later, often through consumption rather than attack. The danger is not constant aggression, but how little margin for error exists. Why ocean life is more lethal than anything on land is not about fear. It is about physics and biology working together. Water hides distance, magnifies force, delays rescue, and gives toxins and wounds more time to act. Land animals tend to injure through visible force that the body can sometimes endure. Ocean organisms often bypass strength entirely and target nerves, blood, or oxygen instead. The question that follows is not which creature is worst, but why the ocean makes even brief contact so unforgiving. The ocean multiplies danger before a creature ever enters the picture. Light bends and scatters, reducing depth perception and masking movement even in clear water. Sound travels faster, but direction becomes harder to judge, removing early warning cues the brain relies on land. The body floats instead of stands, trading stability for constant micro-corrections that drain energy. Every action costs more oxygen than it feels like it should. Human strength is also redefined underwater, and rarely in our favor. Punching, kicking, or pulling loses force as water absorbs momentum and resists speed. Muscles fatigue faster because resistance is constant, not optional. Even trained swimmers experience reduced reaction time compared to running or standing movement. When injury occurs, the body cannot brace or collapse safely. It drifts, sinks, or rolls with the current. Pressure adds another layer that land environments never impose. Even shallow depth changes alter circulation, breathing rhythm, and ear balance. Stress responses increase heart rate just as oxygen availability becomes limited. Pain signals may feel delayed or distorted until they suddenly surge. What begins as confusion can quickly become panic, and panic accelerates everything that follows. Visibility and rescue are inseparable problems in water. On land, injury usually leaves a visible body in a fixed location. In the ocean, currents move victims while they are trying to stay afloat, turning minutes into distance. Rescue teams must locate a moving target in 3 dimensions, not 2. This delay alone can transform survivable injuries into critical outcomes. Water also changes how wounds behave once they occur. Bleeding disperses instead of pooling, making severity harder to assess. Venoms and toxins spread differently through circulation when the body is cold or under stress. Infection risk increases because marine bacteria enter open tissue immediately. The environment continues to act on the injury long after the initial contact ends. These multipliers explain why lethality underwater is often quiet and cumulative. The danger is not always the moment of contact, but what the body cannot do afterward. Humans cannot rest, cannot anchor easily, and cannot wait safely for help. When biology meets physics in this setting, small errors gain weight fast. The question becomes, which encounters exploit these limits most efficiently? Accidental lethality in the ocean often begins with misreading stillness as safety. Many marine animals rely on camouflage or proximity rather than pursuit, and humans enter their space without realizing it. Shallow water feels controlled, familiar, and forgiving, which lowers caution at the wrong moment. Unlike land, where accidental contact is usually brief, water keeps bodies pressed together. The result is danger triggered not by aggression, but by surprise. Needlefish are a clear example of momentum turning into a weapon. These long, slender fish can reach high speeds near the surface, especially at night when attracted to artificial light. Documented injuries show that their rigid jaws can impale tissue rather than tear it, increasing puncture depth and infection risk. The danger is not venom, but the combination of speed, sharpness, and human exposure near boats. Contact is rare, but when it happens, the injury pattern is unusually severe for a non-predatory encounter. Stingrays injure humans almost entirely through defense, not attack. Most incidents occur when a person steps on or near one buried in sand, triggering a reflexive tail strike. The barb can cause intense pain, tissue damage, and in some cases systemic effects depending on wound location. Fatal outcomes are uncommon, but documented cases exist when the barb penetrates the chest or major vessels. The risk lies in proximity and surprise rather than frequency. Reef stonefish represent one of the most extreme examples of passive lethality. Perfect camouflage makes them indistinguishable from rock or coral, especially in shallow reefs. Their dorsal spines deliver venom that can cause intense pain within minutes, along with swelling and potential cardiovascular stress. Without prompt treatment, symptoms may escalate rapidly, making time to care a critical factor. The animal never moves, yet the consequence can be life-threatening. Lionfish add a different layer of accidental danger, especially through human handling. Their venomous spines can puncture skin during reef contact or while attempting removal, a common scenario in regions where they are invasive. The pain is usually immediate and severe, though fatalities are rare. What makes lionfish notable is exposure probability, as divers encounter them frequently in shallow water. Familiarity increases risk, not safety. What connects these animals is not intent, but context. They exploit human assumptions about calm water and visible threats. On land, accidental encounters usually allow retreat and reassessment. In the ocean, the body absorbs the full consequence before the mind understands what happened. This is where accident becomes injury, and injury becomes escalation. Predatory lethality in the ocean often unfolds in a fraction of a second, shaped by visibility and speed rather than intent. Water reduces contrast, blurs outlines, and turns reflective surfaces into signals. Many marine predators rely on sudden acceleration and close-range contact because pursuit over distance is inefficient. For a human, this means there is rarely time to interpret what is happening. Reaction becomes secondary to impact. Barracuda illustrate how misidentification can create risk without aggression. Their attraction to shiny objects and high-contrast movement has been documented in murky or turbulent water. Bites are rare, but when they occur, they can cause deep lacerations due to sharp, slicing teeth. Blood loss in water is harder to control, increasing medical urgency compared to similar wounds on land. The danger is brief, sudden, and often over before the victim realizes the source. Giant moray eels occupy confined spaces where humans place hands or feet without visual confirmation. Most bites happen during feeding interactions or accidental intrusion into crevices. Their teeth are designed to grip and pull, increasing tissue damage rather than delivering a single puncture. While fatalities are uncommon, severe infections and lasting injury have been reported. The lethality comes from proximity and the difficulty of withdrawal in tight underwater spaces. Goliath tigerfish demonstrate how raw bite force becomes amplified in water. Known for aggressive feeding behavior in freshwater systems, they possess large, interlocking teeth capable of removing flesh quickly. Human encounters are rare, but documented injuries show deep wounds that would be easier to manage on land. In water, escape is slower and balance is compromised. The threat is not pursuit of humans, but the consequences of sudden contact. Red-bellied piranhas are often misunderstood through exaggeration, yet their risk profile is specific and contextual. They rarely attack healthy adults alone, but bites have been documented during feeding frenzies or environmental stress. Their sharp teeth can remove tissue cleanly, increasing bleeding risk. Individually, injuries are typically non-lethal, but multiple bites in water can escalate rapidly. The danger lies in numbers and timing, not constant aggression. The great white shark occupies a different category of risk, shaped more by scale than frequency. Attacks on humans are rare and often attributed to misidentification. When they do occur, the size of the animal means even a single bite can cause catastrophic blood loss. In water, managing trauma of that scale becomes immediately life-threatening. The question is not how often this happens, but how little margin exists when it does. These predators reveal a pattern that land environments soften. Speed replaces warning, and water limits response after injury. On land, distance and terrain often provide a buffer after contact. In the ocean, the encounter and its consequences overlap almost completely. This shifts lethality from pursuit to immediacy, setting the stage for threats that do not rely on teeth at all. Chemical lethality in the ocean does not depend on strength, speed, or pursuit. It relies on biological shortcuts that bypass muscle and bone entirely. Venoms and toxins target nerves, the heart, or breathing before pain can even be processed. In water, these systems gain time because rescue and treatment are delayed. The threat is quiet, efficient, and often underestimated. The box jellyfish is one of the clearest examples of chemistry outpacing reaction. Its tentacles carry thousands of stinging cells that can fire on contact with exposed skin. Documented cases suggest venom may trigger intense pain, cardiac stress, and respiratory failure within minutes in severe exposures. Lethality depends on contact area, location, and speed of medical response. The animal does not chase, but the consequence can arrive faster than escape. Pufferfish demonstrate a different pathway where lethality is indirect and delayed. The toxin associated with certain species can interfere with nerve signaling and muscle control. Risk to humans occurs primarily through consumption, not contact. and documented poisonings show paralysis can develop over hours. Without supportive care, breathing may become compromised while consciousness remains intact. Here, danger is not visible in the moment it is introduced. Swordfish appear lethal in a less obvious way, not through attack, but through accumulation. As large, long-lived predators, they can carry elevated levels of mercury in their tissues. Human risk emerges through repeated consumption rather than a single encounter. Mercury exposure has been linked to neurological and developmental harm over time. This is lethality measured in months and years, not minutes. What unites these cases is how they bypass the body's usual defenses. There is no wound to bind, no bite to avoid, no struggle to win. The nervous system becomes the battlefield, and strength offers no protection. In water, symptoms can advance while the threat remains unseen. The question becomes how humans assess danger when the signal arrives too late. Chemical systems also complicate decision-making under stress. Pain may be overwhelming or strangely absent, distorting judgment. Paralysis or weakness can occur while awareness remains, increasing panic and oxygen demand. Treatment often requires specialized anti-venom or intensive care, resources rarely available at the point of exposure. The environment extends the toxin's advantage. These organisms force a redefinition of what lethal means. It is no longer about size or intent, but about how efficiently biology exploits human limits. On land, poisons are often rare or localized. In the ocean, they are integrated into survival strategies across entire ecosystems. And this raises a deeper question about threats that exist even when contact itself is unlikely. Some ocean threats feel more dangerous because they exist outside everyday human experience. Depth, isolation, and unfamiliar biology strip away intuition built on land. These animals are not encountered often, but when they are, the rules change immediately. Lethality here is shaped less by frequency and more by the loss of control. What the mind cannot predict, the body struggles to manage. Anglerfish live in depths where pressure is extreme and light barely exists. Human contact is virtually non-existent outside specialized deep-sea operations. Their danger is not active harm to people, but the environment they represent. At those depths, a single equipment failure can be fatal within minutes due to pressure and oxygen limits. The lethality is indirect, tied to where the animal survives, rather than what it does. Candiru occupy a different category, where risk is debated rather than confirmed. These small parasitic fish are known to enter the gills of larger fish, drawn by water flow. Claims of entry into the human body exist in anecdotal reports, but documented medical cases are rare and contested. Exposure would require specific conditions in freshwater environments. The danger here lies more in uncertainty than probability. Killer whales, also known as orcas, present a striking contrast between power and restraint. They are apex predators with the physical capability to cause fatal harm to humans. In the wild, however, documented attacks are extraordinarily rare, despite frequent proximity in coastal waters. Most serious incidents occur in captivity, where stress and confinement alter behavior. Lethality exists in capacity, not pattern. What makes these animals unsettling is not how often they injure humans, but how little control we retain in their domain. Depth removes escape options, uncertainty disrupts judgment, and scale reminds us of physical limits. On land, rare threats are often distant or avoidable. In water, rarity does not guarantee safety. The environment amplifies consequence when contact does occur. These cases also reveal how fear can distort risk assessment. Humans tend to fear what they do not understand, even when probability is low. Meanwhile, common dangers receive less attention because they feel familiar. In the ocean, unfamiliarity itself becomes a stressor that accelerates physiological decline. Panic shortens breath, and breath is time. As the lens widens, a final contrast begins to form. Some of the most powerful animals pose little direct threat, while smaller systems can overwhelm the body quietly. Lethality is not evenly distributed across size or strength. It follows opportunity, environment, and human limitation. And this sets up a final question about who truly sits at the top of the ocean's danger hierarchy. By the time the great white shark re-enters this picture, the scale of risk looks different than it did at first. Its size and power still demand respect, and a single bite can remain catastrophic. Yet the data shows that encounters are rare, and most sharks pass humans without incident. The danger it represents is immediate, but infrequent. What stands out now is how visible its threat is compared to others. Across this journey, the most lethal forces were not always the ones that chased or attacked. Venoms acted faster than strength, pressure erased margins for survival, and small mistakes multiplied underwater. Many injuries escalated, not because of aggression, but because the body could not recover in time. The ocean reduced reaction windows and removed options that land quietly provides. Lethality often arrived before fear could even form. This reframes how danger should be understood in marine environments. Sharks become symbols rather than statistics, while toxins, infections, and delayed rescue account for far more harm. Humans fear teeth because they are easy to imagine. We overlook chemistry, depth, and oxygen because they do not move or growl. Yet those silent factors decide outcomes more often than predators do. There is also a final reversal that science cannot ignore. While humans fear sharks, it is human activity that poses the greatest lethal threat to them. Fishing pressure, habitat loss, and bycatch kill millions each year, reshaping entire ecosystems. The imbalance is not just biological, it is systemic. The apex of impact does not always swim on fins. Understanding why ocean life is more lethal than anything on land is not about amplifying fear. It is about recognizing how fragile the human body becomes when removed from its element. Water changes physics, biology, and time itself. Respect grows not from panic, but from humility, and the ocean remains what it has always been: powerful, indifferent, and unforgiving of misunderstanding.